All right. Back to work. So let's briefly review what we did so far. We have defined the notion of tree and binary tree. We gave an inductive definition for each one. Inductive. A tree is a pair where we have a decoration and a sequence of trees. It's inductive because in order to define a tree, we refer to trees. The binary tree is similar. A binary tree is either of two things, either a special value that we call null, nil, leaf, empty, zero, or is a triple, where you have again a decoration and two binary trees that we call left and right. So far so good? We look at examples with various terminology like a sibling, a parent, ancestor, descendant. We saw that we can go from a forest of trees, in particular one tree, to a binary tree, and from a binary tree to a forest of trees. We consider a couple of problems. Just to show how to compute the functions, recursive functions, on trees. So far so good? Any question? Alright, so now we consider a spatial breed of binary trees that we call binary search trees. And these are very useful for organizing information when you have to search something. This is very simple, but the way you go to a search engine to look for a page with a certain name is based on this idea. There are billions of pages, and very, very quickly, if you look for something, you find it. And the idea is to use something of this kind. So, what is a binary search tree? First, a binary search tree is a binary tree. So, it's either null or is a triple. Second, there is an order in the decoration. The things that we put in the decoration are a totally ordered set. And the tree has this property. All the decoration in the left child are smaller than the root, and all the decoration in the right child are bigger than the root. And this property is for the root and for every subtree. So here, all the decoration here are smaller than 5. If I come here, all the decoration here are smaller than 2, and all here are greater than 2. A consequence of this is that you cannot put the same decoration in two different nodes of the tree, in two different places. Alright? So what we want to do here with a little bit more precision is how you construct a binary search tree. And this will be done by inserting elements one after another. And how you take elements out from a binary search tree. And this is a relatively complicated algorithm, so we'll spend a little bit of time on this. Alright? So suppose that I have a bunch of values, and I write them in some order. Thank you. 5, 9, 2, 7, 4, 1, 3. Let's see what happens. Thank you. Let's see what happens if I start with an empty binary search tree and I put these inside. All right? So I have an empty binary search tree. I put the 5, what do I get? I get the 5 with 2 empty children on the 2 sides, right? I don't write them there, but these are there. All right, and now I enter 9. What do? I compare with 5. If 9 is equal to 5, which is not, I will say I'm done because I cannot put duplicates there. Otherwise, it's either smaller or larger. If it is smaller, I insert it in the left child. If it is bigger, I insert it in the right child. So now, because this is bigger, I insert it in the right child. Right? Right child. So here I get a 9. Maybe I should put the link to the children here, because it's going to help me a little bit. So now if I insert the 2, what do? Again, I start from the top. I compare with 5. It's smaller, so what do? I insert it to the left. This is empty, so I put the 2, and here I have the 2 empty null children. So now I put the 7 there. Where is the 7 going to be? It's going to be to the right of 5 and left of 9. So I will have here a 7. Then I have a 4. Where is 4 going to end up? Here I will have the 4. Where is 1 going to end up? 1. Where is 3 going to be? Why here? I compare with 5, I go left. I compare with 2, I go right. I compare with 4, I go left. All right? So far so good? So now, of course, you can practice and insert there some other number. Sometimes the student asks me, what if you want to insert there duplicate? How do you do it? Say it again? Pick a side.
To the left of the same one or to the right of the same one?
Not a good idea, because now you start to mess around. Because you have a 5 on the top and another 5 below. If you want to count how many 5s you have there, what do? You have to look everywhere.
You just decide which side you want to go to.
So here, if I want to put another 5, what do? I go left or right of 2? Left or right of 5?
Stick with it.
But then you go right to 2, and then you go right to 2, and go right to 4. It's way down the tree. You have to go all the way to the bottom of the tree at a time.
Right. Every time you have to look everywhere to see whether it's there or not. You have to look a lot. Right. So is there a better idea?
Go to the right. You put them off the
Right. Who said it? Yes.
Just count them.
So here you put a little number that says how many times is there. So all this will be 1, right? When you put it in. And now if I have to put a 5, what do? I change this 1 into a 2. Right? This is just to answer the question. Sometimes students are curious. If I have to do it, how do I do it? This seems a good idea. So how do you search? How can you tell whether an element is in the tree? Suppose that I want to check whether 7 is in the tree. How do I do it? Yes? I compare it to 5 and say, oh, it's not here yet. So what do? Because it's greater, I go down and right, because if it is there, it can only be in the right and not in the left. Yeah? And so I compare it with 9, say it's not here yet. Because it's smaller, forget the right. The only place where it can be is the left. I compare it with 7, bingo, and there, right? If I do it at 6, what's going to happen? 5, I go right because 6 is bigger. I go left because it's smaller. I find 7. I go left because it's smaller. I find that the empty 3, I say, is not here. And so, searching and inserting are very similar operations. You get to some point, and at that point you make the decision. It's either here or I insert it here. How do you remove something from a binary search tree? Say it again?
Very careful.
Very carefully. He's a smart guy. Did you like the talk this morning? Were you at the talk?
No,
No. I thought you were there.
this one.
So, how do you remove? Suppose that I want to remove 1. What would you do here? It's easy. Why? 1 has no children, right? I wipe it out, remains a binary search tree.
Nobody misses it.
No one really is missing it. Very good. And so, if you want to remove something, first you find where it is, and then if you are lucky enough that has no children, disappear. What if you want to remove a 4? Well, it turns out that 4 has only one child, right? When I say only one child, I mean that the other child is the empty 3, right? So what you do is you bring up this other child and everything that is attached under it, right? Here, I could have a 2.9 and here I could have a 3.14. It really doesn't matter. If I am removing 4, I bring this up. All right? And so, if there are no children, very easy. If there is one child, you just readjust the pointers or reference or whatever is your language giving you for that, and bring up the only child. The problem is if there are 2 children, and the simplest example here is 5. If you want to get rid of 5, what do you put there? What would make sense to put there? People are saying more or less. So, here you have to pick what? The biggest on the left child, the largest value on the left child, or the smallest value in the right child. Right? Because this is the closest to that. So here you could put instead of 5 you could put the 7 because it's the smallest of the right child. It's the smallest on all the bigger that are there. So if you put it there, everything still works well. Or the other way around, you put the largest in the left child. Who is the largest in the left child? 4. And so the candidates are either of these 2. Which one? You can even have a consistent policy, or every time you flip a coin and you decide whether it is one or the other. So how do you find, I'll get to that. Very good question, by the way. So how do you find the largest in the left child or the smallest in the right child? Very good. So to find the one in the right child, once you are in the right child, you always go left. You go left as long as you can. So now, if you are here, say, oh, I have to go here, go left, there is nothing to go, so it's 7. If you come here, says go right, there is nothing to go right, so you pick 4. All right? because when you get to this point, there is nothing to go left or there is nothing to go right. This is the situation where you have only one child. So you just pull it up, and everything works like a child. All right? So did I answer your question at this point? All right. So what have we been looking at here? A binary search tree, which is a variation of a binary tree. How is a binary search tree characterized? The decorations have a linear order. If you pick two decorations, you know which one comes first and which one comes second, right? So this is a totally ordered set. And we construct the tree so that all the children, all the decorations in the left child are smaller than the root, and all the decorations in the right child are bigger than the root, recursively. So this is the children of the children, the children of the children of the children, all the way down. Yes? It's a beautiful structure. Which operation you do this? We do search, insert, and delete of values in this tree. Search and insert are very similar. You compare the thing you want to search or insert with the root, and either you are there or you go left or you go right, depending whether the root is smaller or bigger than the value you compare. To delete, we do by cases. If it is a leaf, you just get rid of it, and no one knows. If it has only one child, you pull the child in the position of the value that you want to delete. In main implementation, you just move the pointer. If there are two children, what do? You take the leftmost of the right subtree, meaning you go to the right and then you go to the left as long as you can, or the other way around, the rightmost of the left subtree. All right? Very good. So, now we are going to see a couple of applications of trees. Couple of applications. So one is a decision tree. First, let me give an idea, and then we do an example a little bit more interesting that we tied to running time. Suppose you have three numbers, A, B, thank you, A, B, and C, and you want to pick, say, the smallest of these. Say it again.
Are we turning small from
No. A, B, and C are variables. Inside you have a number. And you want to pick the smallest value stored in these three variables. So, how do you go about the reasoning how to do this? You build a tree. You build a tree where a branch is a question and a leaf is an answer. So, here the question is A less than B? And now you have two possibilities, right? True or false. If A is less than B, you know that B is not the smallest, because A is smaller than it. So here you compare A and C, and this is true or false. If A is less than C, who is the smallest? A. Otherwise, C. And so here, if it is false, what do? You compare C and B, true and false. So if C is less than B, who is the smallest? C, otherwise is B. So this is called a decision tree, and drawing it helps you come up with the algorithm for doing it. Yeah? Of course, if instead of 3 you have a 4 or 5 or 6, all of a sudden you run in trouble. Why you run in trouble? Because the number of leaves that you have and the number of branches is exponential with the number of values that you have to consider. So very quickly this becomes very ugly and very difficult to work. Yeah? But this is useful to solve a number of problems. So here I have a puzzle for you. So, suppose that you have 9 coins, and I don't know why, but the coins are always gold or silver, right? And so, all look equal, all look gold, but the story goes that the king gave to the goldsmith a certain amount of gold to make this coin, and the goldsmith stole a little bit of gold, replaced it with silver. When you mix it with gold, you cannot see. So the 9 coins are not all the same. They all look the same, but one is lighter, because in that one, some gold was replaced with silver. Alright? And so now we want to find which one is lighter. And we have a pen balance. You know what a pen balance is? Pen balance is something like this, where you have 2 arms. And here you have a plate, and here you have another plate. And of course, if you put something on one side and something on the other, we go down by the side that is heavier. Right? This is a very old instrument. It's thousands of years old. Greeks and Romans already had something better than this. What? So I don't know how is the name in English, but this one has still the hook where you hold it, and then has an arm with a heavy weight on one side and an arm with a plate on the other. And so instead of having 2 plates and equal weight, if you move the arm back and forth, yes, a scale. All right, maybe it's called a scale. So this one, in my country, in Italy, is a symbol on the front of the courthouse. The tribunal has a sense of justice that is equal for all. I don't know in this country. It's the same here? So since I came in this country, I become a model citizen. And I didn't have to go to the courthouse so often, so I don't know whether you have it here or not. So, now you have this pen balance, and you have these 9 coins, and we want to know how difficult it is to find which one is not gold, the lighter one. And we see this as a problem of an algorithm, and the running time is the function that gives a number of coins. We could do it for 10 coins or for 20 coins. How many times you weigh this in order to find the wrong one? And then we are going to see whether this algorithm is optimal, what is the average case, what is the worst case, and so on. And in order to do this, we use a decision tree. So this is an application of this. You have any idea how to do this? Yes? All right, so this is not a bad idea. So let's number the coins 1 to 9, right? And so now I build a tree according to your suggestion. We have a tree and we put the coins 1, 2, 3, 4 on one side and 5, 6, 7 and 8 on the other one. And now on the left side I put the case where 1, 2, 3, 4 goes down, and on the right side while the other one goes down. So here I have three options. This one goes down, this one goes down, they are remain even, right? If they remain even, here I write a 9 because this is the one that is lighter. Yeah? If 1, 2, 3, 4 goes down, what is going to happen?
Split 1, 2, 3, 4. I mean, not 5, 6, 7, 8, because one of them is the lighter one.
So if this goes down, one of these is the lighter one, right?
The 5, 6, 7, 8.
Oh, yes, yes. So what do we do here?
Those are the.
We do 5, 6, and 7, 8. And so here I would have the three possibility, but there is no chance that they stay even, right? Because here I have the light one. And so if I come here, what do? I do 5 and... no, 7 and 8. And here finally I have the answer. 7 is lighter, or 8 is lighter. Here I put 5, 6, and I get what?
5 is lighter, so 6 is
5, sorry, this is 8 and this is 7, right? Yes? Yes. And here will be 6 is lighter or 5 is lighter. And here I have a symmetric one of this. All right? So, what is the running time of this one? So, the worst case is that I do 1, 2, and 3 ways. Right? What is the average? Assuming that they are all equally likely, this will be 3 times 4 plus 1 times 1 divided by 9. Yeah? Is the average length to go to a leaf. So, for this one will be 1, 2, 3. For this one will be 3, 3, 3, 1, 3, 3, 3, 3. So, will be 3 times 8 plus 1 divided by 9. This will be the average. Yeah? And the best case is 1. You have to be lucky to get that one. Can we do better than this? So, when do we say that an average is optimal? When you cannot do any better, right? So can we argue that you cannot do any better? If we have 3 possible options, how many leaves do we have? 3, right? How many leaves I have in this tree? 9, 1 for each coin, because maybe the first one, coin number 1 is lighter, or coin number 2, or coin number 3. So in principle, I could have a tree done in this way, where you have 1, 2, 3, and here you have 1, 2, 3, 1, 2, 3, 1, 2, 3, and here I have my 9 leaves, and this one, the running time, both the worst and average, would be only 2. Yeah? Now, does this algorithm exist? Say that again?
You have to split that. You have to have another arm, or you have to do like an odd number every single time, split it into odd numbers.
You should be a lawyer. So there exists such an algorithm. Did you find it?
You just compare 3 coins to 3 coins?
Right. Let's see what happens if we compare 3 and 3. So I start here again, and I do 1, 2, 3, 4, 5, and 6. And here again I have three options, right? They remain level. 1, 2, 3 goes down. 4, 5, 6 goes down. So if they remain level, what do I know? All these are good coins. So the wrong one is either 7, 8, or 9. So here I put 7 and 8 and I compare them. And there are three options, right? If 7 goes down, what's the answer? 8 is the light one. If they remain level, 9. And if 8 goes down, 7 is the lighter, right? So what do I do if 1, 2, 3 comes down? I know that the better coin is either 4, 5, or 6, right? So I compare what? 4 and 5, and I get what? If 4 comes down, is 5. If they remain level, is 6. If 5 comes down, is 4. And the same here. So this is optimal. Why is optimal? How do I argue that you cannot do better than that? Because it was not really obvious that you couldn't do better than the other, right? So how do you argue that this you cannot beat this? And it's something a little bit strong.
The maximum height is smaller than the other three.
Right, but how can you argue that you cannot do, you put I don't know what there and in one shot and you get the other?
This is the smallest tree that can have 9 leaves.
Right, this is a tree that must have 9 leaves. And in each branch you have only 3 ways to go, right? So if you do one level, you just have 3 leaves. You cannot answer for all possible cases that you have. So you need at least 2 levels, right? If I give you 20 coins instead of 9, which kind of tree you need? So let's count a little bit here. Let's try to use a little bit of math. We have 20 coins. Yeah? 20 coins. So if we do one level, how many possible output I have? 3. This is one level. 2 level, how many do I have? 9. 3 level, I have 27. So if I can do it in 3 levels, this is optimal. Why is optimal? Because with 2 I cannot solve the problem. Because it can be 1 of 20 coins, but with 2 I only have 9 possibilities. With 3 I have 27. So in principle, maybe I can make it with 3. In principle. I know that I cannot make it with less than 3 steps. I think that there is a variation of this where you have 12 coins and you don't know whether it is heavier or lighter. You only know that it's different. So you also have to find out whether it is heavier or lighter. And probably you can find on the web a solution until you find it. So far so good? So this is an interesting application of trees. These are called decision trees. These are good only if you don't have too many branches, otherwise you have a combinatorial explosion. This is also a good example of running time because we have an algorithm where the size of the input is the number of coins. The number of steps is how many times you wait set of coins, and you can discuss about the optimality of the algorithm. So sorting, there are various algorithms of sorting, but one can be framed as a decision tree, exactly as I did the example with 3 variables. Instead of 3 variables, you have n. And so, if you build the algorithm as a decision tree with n variables, you can prove, and the proof is not too easy, that the best you can do is n log n. And so if you have an algorithm which is n log n complexity, big O of n log n, then that algorithm basically you cannot do better. You cannot do better if you compare the values. There are some algorithms that they don't compare values one with another for sorting. And if you do this one, you can do better than n log n. Is that so good? All right. So now, last application of trees. Suppose that you have an alphabet. Suppose that you have an alphabet A, where you have 4 letters, A, B, C, and D. As usual, these don't have to be letters of the English alphabet. They can be protein or whatever if you study genetic or anything you want. This is just the way we talk about this. Why? We say that this is an alphabet and those are letters because we are going to consider words over this letter, which are sequences of characters or string of characters. Far so good? Suppose that you want to transmit one of these words, so you encode it in bits, and of course you want to use as fewer bits as possible. So how many bits do you need to encode those? 2. You represent A with 0, 0, B with 0, 1, C with 1, 0, and D with 1, 1. And so now if you have the word A, B, C, what is the string that you have here? 0, 0, 0, 0, 0, 0, 0, 1, 1, 0. All right? So the question is, can you do any better than this? Well, suppose that some letters are more frequent than others. All right? And so here I have an example. Suppose that A comes with a probability of 0.5, B with 0.3, C with 0.15, and D with 0.05. If you are curious, if you add all this probability, you will get 1. All right? Suppose that this is the probability. And now you have to encode this one, A, B, B, A, C, D, A, D, which, surprise, surprise, the letter are written here more or less with their probability. Here there are 5 A's, 3 B's, 1 C, and 1 D, which more or less is what you have here. 0.5, 0.3, 0.15, and 0.05. And now suppose that A you represent with bit 1, B with 0, 1, C with 0, 0, 1, and D with 0, 0, 0. You encode it in this way. Because A takes only 1 bit and comes often, you do better than using 2 bits for each. If you count the bits for this one, you have 17 rather than 20 bits. Yes?
Is the 2 bits instead of 1 bit 0, just to make it like parsable still?
Yes, now we see how you distinguish this. We'll see soon. So you understand what is the problem? The problem is that I have an alphabet, I have words over this alphabet, and in the words of my alphabet, some letters are more frequent than others. So I use fewer bits for the one that are frequent, and more bits for the one that are less frequent. And so at the end, I save some bits. So far so good? So now is, how do I compute, based on the probability, which bits you use there?
So what can other combination tree, you wouldn't ever want to use 1, 1, 1, 1, because that could be A,
Right, so this is a very good point. He says, look, here I encode this one with 0, 0, 0. Could I encode it with 1, 1, 1? And this is not a good idea, because now if you have 1, 1, 1, this could be 3 A's or 1 D. So you see there 1, 1, 1, you don't know which is which. Yes?
You wouldn't want to put 0 you wouldn't want to use 0, 1, 0.
0, 1, 0. No, you don't want it to be 0, 1, 0, because if it is 0, 1, 0, when you see 0, 1, you say it's a B. And then you find that that's a 0 there and you don't know what to do.
Yeah.
So the idea is that as you look at these bits, you know which letter is coming. We can see it here. Here I see a 1. What is this one? A. 1. Now I see a 0. What is this one? So this one is either B, C, or D, right? And so I find the 1, what do I know? B. And so this is a B, this is an A. Now I find the 0, 0. What is the 0, 0? Well, it's either C or D. I look at the next one and I know. So as I go over, I always know what it is. Yes?
Isn't this kind of like the tree itself? Like the way to parse it?
We'll get there. We'll draw the tree in a second. Yes?
Oh, okay.
So first I want to point out that here I have 17 against 20 bits. You can say 3 bits. Who cares 3 bits? Right? What are 3 bits out of 20? 15%. So if you are in any business and you can do 15% better than the business is doing, very quickly you become the CEO of the company. So 15% is a very big saving on everything you do. Money you invest, or gasoline you consume in a car, or anything else. All right? So how do we do this one? So we start with a tree consisting of each letter. So I have a tree. Let me go here. I have a tree made by A, a tree made by B, a tree made by C, and a tree made by D. All right? So now I pick the two with the three with the lowest probability. So the probability are 0.5, 0.3, 0.15, and 0.05. What are the two with the lowest probability? C and D. And so I pick a 0 for the first and 1 for the second. This is a label that I put on my tree. And now this is the tree CD, if I need a root here. I don't really need it, but just to put it. Alright? So now I have this one with 0.3, this one with 0.5, and this one here with 0.2. You with me? This is 0.2. So now I pick the two with the lowest and I join them together. Alright? So I do this one, and this will be the tree B, C, D, the probability of this one will be 5, and here I put a 0 and here I put a 1. Yes? So, which one I put at the 0 and which one I put the 1 is arbitrary. And what I ended up doing, I think, is the opposite of the one that I have in the book, and then we'll fix it. And so now I have these two. These are the only two remaining. So I do this, and this I'm finally done. This is probability 1. This is 0, and this is a 1. Yes? So now, if I want to get the same that I have in the book, let me make a change. And I change every 0 with a 1 and every 1 with a 0. So this will be 1, 1, 1, and this will be 0, 0, and 0. All right? So now, from the root, I go down to each letter, and I put there the bits that I find. So, from the root to A, what I find? A 1. From the root to a B, what do I find? 0, 1. From the root to C, I find what? 0, 0, 1. And to D, I find 0, 0, 0. So, these are my codes. These are the Huffman code in this situation. Oh, sorry, you don't see it and you didn't complain, but you know it. All right? And so, if we look here, we have the character, we have the probability or frequency, and we have the bits that we have computed with this constructor. Yeah? Again? Yes, you can see the tree again. Any question on this? All right, we can review it because it's not trivial. We can review it on Monday. All right. Have a nice weekend.